The world's energy problem has a solution. It's been sitting in front of us for 70 years, and we've been too scared to use it properly. But that's about to change. 7 massive projects are being built right now that could flip the entire energy game on its head. No more coal, no more oil dependency, just clean, abundant power that makes solar panels look like toys. Sounds too good to be true? Keep watching. Let's start in the south of France, where 35 countries decided to build what might be humanity's most ambitious science experiment. It's called ITER, the International Thermonuclear Experimental Reactor. That's a mouthful. The goal? To literally create a miniature sun on Earth. No big deal. Here's the thing about the sun. It doesn't burn fuel like your car. It fuses hydrogen atoms together, releasing massive amounts of energy. You read that right. 10 million. It's the difference between filling your gas tank and carrying around an oil tanker. The problem is, the sun has gravity on its side. It can squeeze atoms together until they fuse. We don't have that luxury. So instead, ITER uses magnets. Really, really strong magnets. These things generate a magnetic field 280,000 times stronger than Earth's. They use this field to contain plasma heated to 150 million degrees Celsius. That's 10 times hotter than the core of the sun, inside a donut-shaped chamber called a tokamak. The French call it a croissant. Just kidding. They don't. Construction started in 2010. The reactor weighs 23,000 tons. That's 3 Eiffel Towers. The facility covers 440 acres. And the price tag, 20 billion euros and climbing. It's the most expensive science project in history, after the International Space Station. But here's where it gets interesting. ITER isn't designed to produce electricity. It's a test. The goal is to prove that fusion can produce more energy than it consumes. They're aiming for a factor of 10. Put in 50 megawatts. Get out 500. If it works, and that's a big if, commercial fusion reactors could follow by the 2040s or 2050s. The skeptics say fusion is always 30 years away and always will be. The believers say we're closer than ever. Someone's about to be very right or very wrong. Either way, France is about to have the world's most expensive lawn ornament, or the blueprint for unlimited clean energy. Now let's head to China. Because while everyone's watching ITER, China decided to build their own fusion reactor. And then another one. And then they casually announced they're building the world's first commercial fusion power plant, scheduled to start generating electricity by 2030. Yeah, 2030. That's not a typo. The China Fusion Engineering Test Reactor, or CFTR, is China's way of saying, we're not waiting around. While ITER proves the science, China's jumping straight to the application. The reactor is designed to run continuously, not in pulses like ITER. It's supposed to generate between 50 and 200 megawatts of power. Enough for a small city, and they want it operational within this decade. How are they moving so fast? Money. Lots of it. China's pouring billions into fusion research with zero public debate about whether it's worth it. No committees. No environmental impact studies that take 5 years. Just engineers and concrete and a government that decided fusion is happening whether anyone likes it or not. They've already set records. In 2022, their EST reactor, another fusion machine, maintained plasma at 70 million degrees for over 17 minutes. That might not sound impressive until you realize most fusion experiments measure success in seconds. Minutes is basically showing off. The thing is, China's not doing this to save the planet. They're doing it because they burn more coal than the rest of the world combined, and they know that can't last. Fusion is their escape hatch. And if they crack it first, they control the most valuable technology of the 21st century. Forget microchips. Whoever masters fusion owns the future. But fusion isn't the only game in town. Let's talk about something that sounds way less sexy but might actually get built faster. Small modular reactors. SMRs. Think of them as the IKEA furniture of nuclear power. Smaller, cheaper, factory-built, and you can plop them almost anywhere. Traditional nuclear plants are gigantic. They take a decade to build, cost $10 billion, and require a small army to operate. SMRs are different. They're about the size of a couple shipping containers. They can be built in a factory, shipped on trucks, and installed in months instead of years. And the price? A few $100 million instead of billions. Suddenly, nuclear power becomes accessible to countries that could never afford the big boys. NuScale Power in the United States is leading the charge. Their design produces 77 megawatts per module. Not huge, but you can stack them. Need more power? Add more modules. It's nuclear power meets Lego blocks. Their first commercial plant is being built in Idaho and should be operational by 2029. If it works, they've got orders lined up from Romania to Poland to countries that haven't announced yet because nuclear is still politically spicy. The genius of SMRs is safety. These things are designed to shut themselves down if something goes wrong. No operator needed. No Chernobyl-style meltdown possible. The reactor core is small enough that natural convection, just heat rising and cold sinking, is enough to cool it. It's physics, not engineering. Physics doesn't fail. Here's the controversial bit. SMRs could be deployed near military bases, remote mining operations, disaster zones, even floating on barges to power coastal cities. Imagine a hurricane wipes out Puerto Rico's power grid again. Instead of waiting months for repairs, you sail in an SMR and have electricity in weeks. It's disaster relief meets energy independence. Critics say SMRs aren't proven at scale. The economics might not work. And oh yeah, you're still dealing with nuclear waste. Fair points. But when the alternative is burning more coal or pretending wind and solar can do it alone, SMRs start looking pretty good. Speaking of alternative approaches, let's head to Canada. Because while everyone's obsessed with uranium, Canada's building reactors that run on thorium. And thorium might be the fuel we should have been using all along. Here's the thing about uranium. It's rare, it's expensive, and it can be weaponized. Thorium is the opposite. It's 3 times more abundant than uranium. You can't make bombs out of it. And it produces way less long-lived radioactive waste. So why aren't we using it? Because back in the 1950s, the military wanted plutonium for bombs, and uranium reactors produce plutonium as a byproduct. Thorium doesn't. So uranium won and thorium got shelved. Oops, the advantages are wild. The reactor operates at normal atmospheric pressure instead of needing massive pressure vessels. No explosion possible. No hydrogen buildup like Fukushima. Just physics doing its thing again. The waste it produces remains dangerous for hundreds of years instead of tens of thousands. That's still not great, but it's a lot better than what we've got now. Terrestrial Energy is partnering with Ontario Power Generation to build the first commercial thorium reactor. Target date is early 2030s. If it works, Canada becomes the world leader in next-generation nuclear. The catch: thorium reactors are unproven at commercial scale. The technology works in labs. Whether it works for 40 years straight powering a city is a different question. But hey, you don't revolutionize energy by playing it safe. The Natrium reactor, funded partly by Bill Gates because apparently, billionaires need hobbies. Natrium, built by TerraPower, is a sodium-cooled fast reactor paired with molten salt energy storage. Let's unpack that. Traditional reactors use water to cool the reactor core. Natrium uses liquid sodium. Sodium stays liquid at much higher temperatures than water, which means the reactor can run hotter and more efficiently. More heat equals more electricity from the same amount of fuel. But the really clever bit is the energy storage. The reactor produces a steady 345 megawatts. When the sun's out and wind's blowing, Natrium runs at base load and stores energy. When the sun sets and wind dies, boom, release the stored energy and keep the lights on. It's the best of both worlds. The first Natrium plant is being built in Wyoming, replacing a retired coal plant. Same site, same workers, cleaner energy. Construction should finish by 2030. If it works, it could become the standard design for replacing coal plants worldwide. And there are a lot of coal plants that need replacing. The risk: sodium is reactive. It explodes on contact with water. So if there's a leak and it rains, you've got problems. It's not a power plant. It's a research reactor that will prove whether waste-eating reactors can work commercially. If they can, we solve 2 problems at once. We get more energy from fuel we've already mined, and we dramatically reduce the waste storage problem. Countries like Russia and India are already operating fast reactors. The US is late to the game, scheduled for completion in the late 2020s. could catch America up. And once the technology is proven, commercial reactors could follow within a decade. Imagine this. Every country with nuclear waste, and that's most of the developed world, suddenly has a new energy source sitting in storage pools and concrete casks. Waste becomes fuel. The economics flip completely. Instead of paying to store waste, you get paid to burn it. That's the dream anyway. The challenge is that fast reactors are more complex than traditional ones. They run hotter, use more exotic materials, and require more careful monitoring. But if we're serious about solving both the energy crisis and the waste problem, the kind of big that makes ITER look modest. Most fusion projects are thinking small, scale up later. Polaris is thinking the opposite, go big immediately. The logic is that fusion only makes economic sense at massive scale. Building a small fusion reactor is like building a small skyscraper. All the complexity, none of the benefit. Polaris aims to generate 1,000 megawatts of electricity by the early 2040s. That's enough to power 1 million homes. The design uses a different approach than ITER's tokamak. It's called a spherical tokamak, which is more compact and potentially more stable. Think of it as the difference between a donut and a cored apple. Same idea. Tighter package. The UK is betting big on this. They've committed billions in funding and partnered with private companies to accelerate development. The timeline is aggressive. Site selection by 2025. Construction starting around 2030. First power by 2040. For context, that's faster than any nuclear project of this scale has ever been completed. Why is the UK going all in on fusion? Brexit? No, seriously. After leaving the EU, the UK lost easy access to European energy markets. They need energy independence, and they need it fast. If it works, the UK becomes the Saudi Arabia of clean energy. If it doesn't, they've got a very expensive monument to ambition. The critics point out that we don't even know if fusion works economically yet, and we're already designing gigawatt-scale plants. It's like designing a 747 before you've proven that wings work. Bold? Absolutely. Reckless? Maybe. But safe bets don't change the world. Here's what connects all 7 of these projects. They're being built right now. Not in some distant future. Not in theoretical papers. Actual budgets, actual timelines. ITER is assembling. China's CFTR is rising. NuScale's SMR is taking shape in Idaho. Natrium is breaking ground in Wyoming. The versatile test reactor is being fabricated. And Polaris has moved from concept to funded program. These aren't pipe dreams. They're concrete and steel and superconducting magnets and tens of billions of dollars in committed funding. The question isn't whether we can build them. We're already building them. The question is whether they'll work as promised. They don't all have to work. If even 2 or 3 of these projects succeed, the energy landscape changes completely. If SMRs prove economical, coal plants start shutting down faster. If thorium reactors deliver on their promise, nuclear becomes politically easier to sell. If natrium's energy storage works, renewables and nuclear become partners instead of competitors. If waste-eating reactors pan out, the storage problem shrinks dramatically. And if fusion, either ITER's approach or China's or the UK's, finally breaks even, we're looking at a fundamentally different civilization. Fusion especially changes everything. With fusion, energy becomes nearly free. Not literally free, but so abundant and cheap that it stops being a constraint on human activity. Desalination becomes trivial. Water scarcity disappears. Carbon capture becomes affordable. Climate change becomes solvable. Energy-intensive manufacturing returns to rich countries because electricity costs nothing. The geopolitics of oil and gas evaporate overnight. That's the prize. That's why 35 countries are funding ITER even though it might not work. That's why China's racing ahead even though fusion has disappointed for 70 years. That's why Bill Gates is betting his fortune on Natrium. The upside is civilizational transformation. But let's be honest about the risks. Nuclear projects have a history of running over budget and behind schedule. ITER was supposed to cost 5 billion euros. It's now at 20 billion and counting. First plasma was supposed to happen in 2016. Now it's scheduled for 2025. Maybe. These projects could fail. The physics might work in theory, but fail in practice. The economics might never pencil out. Public opposition could kill projects before they're finished. And even if everything works technically, we still need to train thousands of nuclear engineers, build supply chains, establish regulatory frameworks, and convince the public that this time, really, nuclear is safe. That's a heavy lift. We keep burning fossil fuels and watch the planet cook. Or we go all in on renewables, and accept that we'll need to carpet vast areas with solar panels and wind turbines, while hoping battery technology improves fast enough to handle the storage problem. Neither option is great. Nuclear, for all its baggage, offers a third path: concentrated energy production on small land footprints with zero carbon emissions and fuel supplies that last centuries. It's not perfect, but it might be the least bad option we've got. These 7 projects represent different bets on how to get there. ITER bets on international collaboration and taking time to get the science right. Thorium bets on better fuel. Natrium bets on hybrid systems. Waste-eating reactors bet on closing the fuel cycle. And Polaris bets on going big immediately. They can't all win, but they don't all have to. The energy transition isn't winner-take-all. There's room for multiple technologies. We'll probably end up with a mix: solar and wind, where they make sense. SMRs for remote locations and developing countries. Large reactors where grids need stable baseload power. And eventually, if we're lucky, fusion for everybody. The timeline is the next 20 years. By 2045, we'll know which of these projects delivered and which ones flopped. We'll know if fusion is real or still 30 years away. We'll know if SMRs captured the market or got undercut by cheaper alternatives. We'll know if thorium lived up to the hype or stayed a footnote in nuclear history. What we're watching is the future being built in real time. 7 different paths forward. 7 experiments in how to power civilization without destroying it. Some will fail, but if even one succeeds, we'll look back at this moment as the turning point. The decade when humanity finally figured out how to generate clean, abundant energy at scale.
That's the game.
It's anybody's match.